Welcome to Graph Theory, lecture number one. Let's get her started. Should be exciting day, maybe. Who's to say? It's all right. So what are we gonna talk about today? Well, basically, what we're gonna do is kind of go through just some basic slides, syllabus, first day kind of stuff. All that good stuff. Have a little fun with that. Then we'll get graphing. I guess is what we'll do. Uh, really, so we're just today. So obviously I sent the email with websites. You probably took a look, took the lecture notes and whatnot. Really, today, really the first couple days. Well, I wouldn't say just the first couple days. There's going to be a lot of days where all we're talking about is defining this, defining that. This is a theory class. Remember that. So there's going to be a lot of definitions, a lot of proofs, a couple algorithms. Yeah, just the taste. If you want a lot of algorithms, take graph mining instead. Where I just came from. You know, we had some fun with that. Connectivity algorithms. It was a good time. So obviously, here's the website. Tentative schedule. Probably going to be sticking to this pretty close. Yeah, this is my sixth time teaching this class, I think. So I kind of got a good feel for how long things take. But I think COVID last time threw things off. So maybe this is all wrong. So I copy pasted this from last semester. The difference was less. So normally when we're in person, we do our quizzes in class as like a collaborative thing to kind of force you to think about it, think about stuff, think about things. Uh, but with virtual, I had the quizzes after class. What I'm saying is schedule's probably good, but it might not be, locked in as fixed as it will be. But I think, as it is now, I like it. I think it's good. So we're gonna try and stick to it, is what I'm saying, in terms of the schedule. Okay. If there's any questions as well, just hit it up in the chat. I think you should be able to do that. I should be able to see when it pops up. So the last time, since I used WebEx last, they've changed some things. One of the things they changed is when someone puts something in the chat, I'm sharing my screen, it shows up slightly longer. So it's actually possible to read, because before it would show up for a second, then immediately disappear. And it's possible to have the chat on your screen as you're sharing. So, it's what I'm saying is I can actually read, see it when you type stuff now. So I'll be able to answer any questions. So probably will be questions. So if you have any, just throw them in there and we will address them. So, okay. I guess first things first, let's talk syllabus. We've got some slides here that I made. Syllabus slides, I guess, first day syllabus-y kind of slides. Which we'll just kind of go through, I guess. So one thing though, so I don't think that'll still apply to anyone here. So a number of people emailed me asking if they could get signed into the class, and I said just bring the form on the first day, and that was before it went virtual. So if you know anyone that was going to do that, I think people will drop anyways. So I don't think it'll be a big deal. They should be able to get anyways. But if you want to switch sections, if you want to switch to math or anything, just let me know. I apparently can now override to let you register for math, even if the math section is full. So if that's the case, or if the CS section is full, just let me know and I'll be able to do that. Just send me an email. I'll be able to do the override for you. It's a brand new feature in SIS. I can't actually add you to the class, but I can override to let you add yourself. But only if you're already in the class, apparently, because I can't do it. I can only do it for students currently in my classes, or students of which I am an advisor. So it's very functionality is limited, but it's progress. Didn't have that 6 years ago, but now we do. And used it once already, so can't wait to use it again. Okay, so let's get started. Course overview. So just gonna quick about me, about the course, general facts. One of those facts is no longer applicable. I forgot to change out. One of the things I was gonna do was change it, but I forgot. So, anyways. Okay, so, you know, teaching graph theory ever since I started here at RPI 6 years ago, back when I was a young boy. But, now I'm an old, grizzled veteran, so I no longer have an excuse for doing a terrible job. So, unfortunately, maybe I'll do a decent job. I don't know. We'll see. We'll see how it goes. I think I've definitely have done a lot better than that first year. So, I think I've mentioned this other classes I've taught if you've taken anything else. The derivative is good. So that's the, even if the value is bad, with the current t, the derivative is good. So that's what's important. So office hours, right after class. I'm going to have them in my office right after class on the days that we have class when we're actually, in person. Otherwise, WebEx. Yeah, so, if you want to do WebEx, just send me an email, set up an appointment. My research interests mostly is not so much graph theory. I do a little bit like graph generation and, some connectivity stuff and this and that. I touch on it. I've written a few proofs in my time. But mostly I do like large scale graph analytic, graph mining kind of stuff. A lot of HPC, scientific computing. So scientific computing is a bunch of like, scientific problems. Pretty much all of scientific computing, if you're doing like either weather simulation or physics simulation, this or that, it's going to be on a mesh of some kind. And a mesh is really just the graph. So that's where I come into play. I do some graph stuff on that mesh for you and, let you compute your science. At least in that, that's what I do for that. Generally it's a bit more applied than theoretical, but, I teach graph theory anyways because they told me to. So here I am. If you want to take more applied stuff, more algorithms, and more interesting real world problems, take graph mining. Still time to sign up. You might have missed the first class, or you just came from that class. But you can never have too many graphs in your life. What other stuff? Climb, ski, general sending of NAR. Don't really, but I like to think that I do. Get some sixth sends out there, but it's really, I'm just bad at everything. So that's life for you. That's life. So, okay. So we have a TA and two mentors. Two mentors is new. We had one mentor last time, so take advantage of that. Generally, I would say your first stop for help with problems on the homeworks is going to be the mentors, because they've taken this class, and especially Chris, he both took this class and is currently on, second time mentoring. So yeah, he'll probably be pretty solid for you in terms of helping with homeworks and stuff. He's been around the block a few times, so he'll do, he'll treat you right. The TA probably also be all right too if you have, you can't make any of the other hours, because she was TA last time and she did a good job. But her primary responsibility, is going to be grading. So, to keep her, on track with grading, because she's going to be doing a lot of grading. Probably, hit up the mentors first stop. PA office hours probably be more for like grading issues, questions after the fact. I think would probably be the best use of her time for that. But since we have two mentors, I'd say use them for homework problems, homework questions. So all this is, they're all going to be virtual all semester. I think that's standard policy for now. So, and probably not going to change this semester, but I think that policy might change or something in the fall. Yeah, I've got some course mascots, got a dog and some chickens. Dog might chime in during these virtual sessions. Chickens. So last year, birds, is in a different place. They like to hang out pretty much at the window and just scream at me. No longer the case. No longer have a window with birds screaming at me. But the dog still likes to scream at me, just in a different kind of scream. More of a bark, I suppose. But, what's the purpose of having course mascots? There is none. But the slide existed, and I kept it. So here it is. So generally, what's the course? Who's to say? It depends on where you're coming from. If you're in CS, it'll be a lot of theory for you. If you're in math, there'll be a lot of algorithms. I mean, so there is some algorithms, but there isn't a ton. But for like, any arbitrary math class, there's a lot of algorithms, I would say. If you're in any other major, you're here because who knows? But who's to say? I don't know. Why am I here? I don't know. I'm here because graph theory is an important course to teach, I guess. So really general overview of the course, it's mostly pure graph theory with some amount of graph algorithms. Obviously, we got the website there. The textbook, Introduction to Graph Theory. So, hopefully you didn't buy it, or, you could buy it and support Douglas B. West in his pursuits. But something you should know, completely irrelevant to anything in particular. If you would say go to Google and type, in quotes, title of something, some arbitrary thing, file type, PDF, stuff will show up as a PDF with the title of that title of something that you have in quotes. So that is irrelevant to anything in particular here, so whatever. I don't know why I said that. I said that for no reason in particular. So that's just something to know, information you should know. So the schedule, like I said, let's just see the website. Gotta try to keep track as much as possible. I think we should be able to do a decent job with that. Yeah, so the website will have WebEx links first 2 weeks, password SP22. So all the homeworks are going to be collected via Submiti. Just have you convert to PDF and upload it. Really, how that's going to happen. The first couple quizzes are going to be collected via Submiti as well. Generally, quizzes, as I mentioned, are going to be done in class in a collaborative fashion. They aren't real quizzes, so the purpose isn't to quiz you. It's to really just make you do something, force you to actually think about the stuff we just talked about. It's kind of, reinforce the concept, really, in class work. It's more what it is. But they've been traditionally called quizzes, so I just kept it as is. So, yeah. After office hours would be remote because of the COVID stuff. Non-cloth masks required in class. It's standard RPI policy. So, of course, I don't know what policy that is. Someone's policy. So surgical mask / N95s or variants thereof. So your grade. So this again, more syllabusy kind of stuff. So if you took the class because you heard last time there were no exams, hate to break it to you, but there's going to be exams. So normally there always has been, and there always will be, except for when the class is fully virtual, because I didn't want to deal with that nonsense. Having virtual exams. So we're going back to exams. We're going to be, first one is going to be in class. The next one's going to be during finals week. So basically grades is going to be 40% homeworks, pretty much bi-weekly problem sets. So pretty much every 2 weeks, we're going to have a new problem set. So in total, probably have 6 to 7, depending on how things go. Submit via Submiti. Usually going to try and give you around 2 weeks to complete them. So release them on 1 week, probably a Monday. They'll be due in 2 Fridays. So approximately 2 weeks, not exactly 2 weeks. I'll try and give you 2 weeks, but see how it goes. 3 late days total. It's going to be the policy and Submiti. Nothing else accepted beyond those late days. Max 2 late days per assignment. So the reason why 2 days, because I like to go over the assignments over the next class. And they're probably going to be due on Friday. So plus 2 late days Sunday. So on Monday, we could talk about the assignment in class. So I'm generally not going to accept anything after we've already talked about it in class, because that would be, that'd be whack. So, that's how it's going to be, I guess. Quizzes. So Generally, it's going to be every Friday. We're going to have a quiz, or not Friday, Thursday. Thursday class, we're going to have a quiz. Usually last 20, 30 minutes of class is going to be devoted to the quiz. So during virtual, I'm just going to assign it and have you do it and give you 24 hours. So do like on Friday or something. So just release it after class, have it due, the next day. Normally, so when we go back to in person, I'm just going to hand it out. I'm going to work on it in class, so collaboration will be allowed fully for quizzes. So you can talk about it with everyone in your vicinity, or, you can yell across the room if you want. Never seen it, but, it's, well, I don't know. That, we'll see what happens. Might have to calm things down if things get out of control. I don't know. So collaboration is allowed for quizzes, also for homeworks. So my thought with this is people are going to be collaborating anyways, even if I say you can't. So, by saying you can't, I'm only going to be punishing the most honest among you. So everyone can collaborate. That's kind of what I'm saying here. But you still need to do the problems on your own, meaning you can't just directly word for word copy someone else's stuff. So, that's, yeah, you still have to think about it. So the whole point of the quiz is to make you think about it. So, you still got to think about it. So the other 50% of the grade is going to be exams. Like I mentioned, the midterm is going to be the last day before spring break. That'll be 20%. That'll cover the first approximately, I don't know, 3/8 of the course, give or take. I don't know how you define fractional percentage, but the first 3 chapters. So we're going to be talking about stuff, I don't know. The first, I don't know. Let's not talk about that in terms of fraction, but less than half the material is going to be on that midterm, which is why it's weighted as is. Then the final, during finals week, so that's going to be pretty much the rest of the class. The rest of the material in the class is going to be on the final. But since everything builds off of everything else, there's probably going to be some, you're still going to have to know the initial stuff because it's going to have a lot of definitions and whatnot that are going to be from the initial part of the class that are going to make their way onto the final. Everything builds off of everything else, so you should still be familiar with everything. I'm probably not going to ask you the algorithms or specific proofy stuff for the first part of the class and the final, but there's going to be definitions and such that are going to show up just out of necessity. Maybe, I don't know. Maybe I'll make it comprehensive fully. I don't know. Probably not. I'm probably going to weight it more towards it's going to be heavily weighted towards the second half of the class. This class is full. Sign form, like I mentioned. We have the brand new feature in SIS where I no longer need to sign a form. I just hit up the SIS and override if you're already in the class, I guess. I guess I do need to sign a form if you wouldn't be here listening because you aren't in. So sorry for those guys, I guess. Whoever emailed me asking to get signed in. Yeah, so anyway. So if you want to switch to the math section or something, I could do that for you. I could do that for you. That's about it. Or if you're one of my advisees, I guess I could sign you in technically. So if you missed assignment, they can't turn it now. Yeah, if it's a school department approved absence, and same thing with quizzes, if it's approved excuse, what's an approved excuse? If you get in a car accident or in a coma, I'll approve that. That'll be approved readily. If you overslept, if you're hungover, can't give you approval for that, so unfortunately. But, and then you obviously got the late days, but no late days for quizzes. Quizzes will not be accepted late because they're going to be in person, really. And they're going to be pseudo in person for this virtual stuff. You're still going to have to, still I give you 24 hours to do it. That's more than enough time. That's suitably long because the whole point is going to be, you do it immediately. There's a Discord or something for these first 2 weeks. Get on that and chat away, collab on the quiz. The quizzes are probably going to be pretty easy for these first couple ones, at least. The quizzes are never tough. Once we actually get into the proofs, there might be a couple brain busters, as they call them. But for the first couple ones, not gonna be busting any brains, I guess. So how are we doing office hours? So I already mentioned that, but I still get questions. So it's here again. Yeah, so that's the slides. Okay. Any questions, hit the chat. Let me just check. So I have to, in order to see if there's any questions that in the chat that I missed, I have to stop sharing. So that's why I'm stopping sharing right now. Looks like nothing in the chat. Well, pretty quiet group here today. Yeah. Taught graph mining right before this. Throats. Already said so many words. Throats hurt. Plowing through here. A lot of words that need said, I guess. So like, oh yeah, let's go through the syllabus too. I gotta put this back in upright mode. Get through this. So this has all the deets. I don't think there's anything extra here, but let's just go through that I didn't cover in the slides, but let's just go through to see, course description. I mean, the prereq, so you shouldn't have been able to sign up for the class. You don't have the prereq. So this is going to be, really the importance is because we're going to be doing a lot of proof stuff, a lot of like set notation. So all the graph stuff is going to be borrowing like set notation. So you should have a passing familiarity. I'll try and redefine stuff as I go, but can't guarantee anything here. Might be jumping over this and that. But because we're going to be doing a lot of like, we're going to be doing inductive proofs and such with a different kind of flavor though. It's gonna be different. It's gonna taste a little different. You get the taste of graph theory induction. It's doing strong induction tastes a little different than the weak induction you've been doing already. In Fox or FOA. I don't know what the math people call that. I guess FOA, FA, maybe. I don't know. But yeah, so I don't know. Should have that kind of back. I should have been able to sum, of course you did, but so we are going to be talking like, algorithms and such. Even if you come from math background, it shouldn't be too bad, I don't think. You should have a passing familiarity. I would recommend that. Having like a passing familiarity, like a CS1 level familiarity with like algorithm, like, description. Be able to, if like you look at pseudocode, being able to follow it, you should be able to do that. You aren't going to need to write any code. I might have, I'm going to have some examples in the mix where I like use NetworkX and, implement some algorithms and such. But, beyond that, it's aren't going to be, I say very useful, but yeah, I'd say very useful. I'd stick with that. So I got the book, get it wherever books are found. So I'd say it isn't absolutely necessary to get the book, but you still should. Like, it's useful. It is useful. Generally, everything in it, there isn't going to be anything that you need to know that's in the book that I haven't already like pretty much put within the notes or like cover in lecture, but it still might be useful because with like the algorithm descriptions and like the proof approaches, they're all going to be slightly different. I think they're worse in the book, in my opinion. The author, Dougie B, as I call him, he's very much a math kind of person, so the way he writes algorithms is bad. I don't want to say bad, but not ideal for like people with a CS background. And like the proofs, because like obviously he didn't want to write 1,000-page book, so the proofs are pretty condensed. So the way we cover them in class is going to be very much expanded and a bit more detail. So but it's still good to have the reference back in case I miss something or I misspeak, which happens on occasion. Happens frequently, I'd say, frequently on occasion. Exam stuff, all that's blah blah blah. Grade modifiers, standard stuff. Curve policy. So generally I just do a flat curve. So none of that fancy stuff. I don't do any of that fancy curving, fancy curvature. Just be like, okay, the average on the exam was 70. I think an average of 80 would be good. So everyone gets plus 10 points. That's how I do it. You know, it's yeah. But basically, so if you're very much at the tail end of the bottom, you aren't going to get much boost. That's all I'm saying. I think the first exam probably isn't going to be too bad. The final exam is going to be bad. I will say that right now. Usually it is pretty bad. Usually that's where I throw the brain busters down. I really bust some brains with that. So, but yeah, that's but usually, I'll give a curve. So the average grade on any exam is not going to be lower than 80, is what I'll say. So I'm not, the intention here isn't to make, so you should be able to get full credit on, close to full credit on the quizzes and homeworks because you are allowed to work collaboratively. There's more than enough resources online. And, if you have access to past homework solutions and past whatever's, you should probably be able to hit that up. So you should be able to get a significant amount of credit for the homeworks and quizzes. So, still, even if you have access and there's a similarity between a problem that exists in the homework and problem question you see with the solution online, you still work through it because that'll help you with the exams because you won't have access to any of that in the exams, and the exams are half your grade. So that's why we have exams, because graph theory's been around for 150, more than hundreds of years. I don't know. When was Euler, poking about? I don't know. I think it's 1800s maybe. So it's been around. So basically everything that can be asked in terms of a question for graph theory has been asked and has found its way onto the internet. I don't know. There's some slow to specials to throw in the mix that, you won't be able to find, but who's to say? Okay. So collaboration, like I mentioned, allowed for quizzes. I say partially allowed. I think, fully it's allowed for quizzes and homeworks. Completely forbidden on exams, obviously. Still do the homework on your own. If not, academic integrity, boilerplate stuff here. Policies for a healthy learning environment. Just be cool. Be tolerant of other people, or I will banish you from the class and fail you. It's zero tolerance policy. I don't know if I can banish you forever from the class. I don't know if I can, but maybe I can. Never had to do that, but I reserve the right to attempt it. But yeah, could have. For me, I am allowed to just fail you if you're like harassing someone in an inappropriate way or something. Never had to do that. I don't know. So I think most all of you are pretty chill and good people. So I never have to do that. But I reserve the right to banish it forever. Send you out onto the river. Like in that one Batman movie. Banishment by whatever, or punishment by banishment, whatever that was. If you understand that reference. So you'll learn stuff here. Mostly you'll be learning proof techniques for graph theoretic, and so a couple graph algorithms in the mix. Most of what you're going to be learning that you haven't already seen. A lot of the algorithms, if you've taken like algo, you've already seen. So we're going to talk like shortest path, minimum spanning tree kind of stuff. But the proof techniques you haven't seen, or maybe some, who's to say? I don't know what they do in FOA, in the math side of things. I really don't even know what they do in Fox, to be honest. I've never taught it. Never really looked at detail in the syllabus, so I don't know. But yeah, so you learn, most stuff you're going to be learning is proof techniques for proving graph theoretic stuff. So that's that. Yeah. Okay, so let's actually get lecturing. So the lecture notes here, you can load up. So generally we're going to have like this kind of stuff that shows up. So I have everything kind of written out. So this is really just the most important stuff extrapolated from the text, from the relevant portion of the text, West chapter 1.1, as we see here, as well as with some additional details that I like to state. So I like to talk real graphs, put everything in context a little bit here. I like to talk graph representation. So I don't know how much detail really the graph or the book gets into in JCC matrix stuff. I know they don't talk about like compressed sparse row format or like adjacency format, but from the computational side of things, if you're going to be working with graphs, you're probably going to be using like either adjacency format or compressed sparse row format of some form. And so adjacency matrix is like sparse representations of adjacency matrix. It's really just the compressed sparse row format of a matrix. So, like if you're working with an adjacency matrix, what I'm saying is it's going to be compressed sparse row format anyways. But I mean, you could have a graph specific compressed sparse row format or adjacency format. Okay, we'll talk about that in a bit. Probably not going to talk about compressed sparse row stuff. But that's just there for, to tickle your noodle. Or I shouldn't, definitely shouldn't say that. I meant brain noodle. Sorry. Okay, so let's just get started here. All right. Okay. So our in-person class is going to be recorded as a question. So tentatively, I'm going to see if I can do that. So no matter what, I guarantee the notes that we write are going to be posted. That is guaranteed. Well, I'll see how we do. So really, I might just take this webcam and to class when we're in person, hook it up to this tablet. And I'll be writing stuff on this tablet and be recording, I guess. I might just do that and see how that goes. So that's tentative yes, but we'll see how it goes. We'll see how it progresses and such. Okay, so what am I even doing here? All right, so let's lecture 1. Cool. Let's get her started here. I can make, I thinned it up for graph mining. I'm going to thicken her up again. So let's talk graphs. So what, you might be asking yourself, what is a graph? Really, if you're asking yourself this, and you signed up for graph theory, I got some questions for you. It's interesting is what I'd say. So what is graph? You got your x-axis, you got your y-axis, you got your bars, you got this, you got your chart. That's a graph. No, wrong. Shut that down right now. That's not the kind of graph we're talking about. But you're gonna go tell your mom you're taking graph theory, and if she isn't like doesn't have a mathematical background, she went to business school or something, she'll be like, oh, you're taking a whole class on bar graphs? What? No. Tell her she's a fool. Tell her what a graph is. We're going to get into a more formal definition in a second here, but really think of it in terms of a discrete object, a set of discrete objects connected by, defined with the set of relational discrete edges. So really we have vertices connected relationally with edges. So really a graph defines some set of relations between discrete objects. So we have a set of vertices, a set of edges. So we kind of we'll get into like more formal definition in a second. But to give you some context, so yeah. So there's a lot of, kind of subset. Like we'll get to it. But to give you the context here, like a lot of this, real world kind of graphs. So really, every single thing is a graph, no matter what. You can't give me one single thing that is not a graph. Why is that? Because everything is at least a discrete object. Anything that exists is a discrete object. We have just a single vertex. A single vertex, guess what, is a graph. You have multiple objects, multiple discrete entities. It'd just be a graph without edges that have no relation to each other. It's still a graph. Boom. Blew your mind. All right. But really everything, is relational. Any kind of data set can be represented in a relational way because you can define relationships with anything. really. What are the common kind of relations that we discuss when we're talking about graphs and graph applications? Well, so, one of the big dogs, social networks. You got your boy, Bob. Got your boy, Joe. You got your girl, Karen. Well, guess what? Bob is friends with Karen. Bob's friends with Joe. We got ourselves a social network graph defining a relation between Bob, Karen, and Joe. You got the discrete objects, discrete entities, Bob, Joe, and Karen. You got the relations defined between them. Got a relation between Bob and Karen. We got a relation between Bob and Joe. There we go. We got ourselves a graph, which is, in this context, a social network. We could have, say, a road network. So we got Troy here. We got Albany down here. We got Schenectady. Let's just shorten that up there. Yeah, we got a highway going from Albany to Troy-ish. Got a road that goes from Troy to Schenectady, the Troy to Schenectady Road or whatever it's called. And we have a road network. So we have a road between Albany and Troy and Schenectady. I mean, really, there's roads between Albany and Schenectady as well. So, maybe there's intermediate towns along the way, whatever might be there. I don't know, Latham or something. Who's to say? Really, Latham's between Albany and Troy, too. I don't know. Whatever. Okay. And then, we have I'm just giving you some examples here. Social networks, road networks, and let's say information networks. Info nets. Don't have enough space to type out either of those, so we'll just do information networks. And so what we could have here is, say, a web page. So the internet itself, believe it or not, is a graph. What is it? It's an information network. Defined by what are you doing here? Okay. I don't know if that popped up for you guys, but that website A connected to website B. How? Via a hyperlink. Nice. Not just a link, but a hyperlink. Why are they called hyperlinks? I don't know. But, the internet, guess what? It's just a graph. It's a big graph. It's multiple zettaflops or something of a graph, but it's a big one. Doesn't get much bigger than that in terms of graphs, I don't think. On the notes, I list some properties common to. So these aren't super relevant for the class, but I always like to discuss them anyways. Always nice to get a taste for the real world in a theory class. Real world worlds, real world graphs. So it's always nice to get a taste. Properties of real world graphs. So that's kind of have listed up there in the notes. We have this property of sparsity. So if you're coming here from graph mining, we're kind of repeating stuff, but just this, and then we'll get into this. Well, we're going to repeat some stuff with the basic definitions too. But I don't know how many people have taken both. That's a lot of graphs, for one day for you. It's a lot of graphs for me. That's all I do. So it's whatever. So sparsity, what sparsity is referring to is essentially just, so here's where the set notation comes into play. And this E and V, which we haven't defined yet, but essentially E is the set of edges within a graph. V is the set of vertices within a graph. And the arrow is essentially saying that the number of edges, the cardinality. So the notationally, when we put the bars around the set, we're saying the cardinality of the set, which is essentially the number of, the size of the set, the number of things within the set, more or less. So the cardinality of the edge set is much, much less than the cardinality of the vertex set squared. So what does that mean? So approximately the number of possible unique edges within a graph is proportional to the cardinality of the vertex set squared. Really, it's cardinality of vertex set minus 1 times cardinality of vertex set over 2 number of unique edges relational pairs within the graph in terms of the number of vertices within the graph. So essentially this is saying that the number of possible edges is much, much less than the number of possible vertices. And so, if you think about any social network, Facebook has 2.5 billion people on it, I guess. The number of how many friends do you have proportionally to that 2.5 billion? Probably not in the billions. Probably maybe not even in the thousands. So the number, consider the sum overall possible users. Is the number of total connections is going to be much, much less than the number of possible total connections. Essentially what it's saying. We have the property of skew or degree skew. So basically, the number of, I don't know, easiest way to say this, number of low degree vertices is much, much less than number of high degree vertices. So shorthand for vertices is just verts. So if you haven't figured that one out yet, that's what that is. So essentially we talk about the degree skew. So the degree of a vertex, we'll get into this more detail later. The degree of a vertex is the number of edges adjacent to that vertex or incident on that vertex. So when we talk about incident edges, essentially you have a vertex, any edge that's attached to that vertex, we would say is incident on that vertex. So the number of low degree vertices in a network is generally going to be much other way around, much, much greater. When you're doing it, separating these out over lines, it gets confusing. Much greater than the number of high degree vertices. And this is just, we talk about skew. Essentially what we're saying is most vertices within a network are going to have a degree towards the lower end of the average, towards the lower end, in general, versus the number of high degrees. So think of Twitter or anything like that. Number of, if you consider users on Twitter, most people are only going to have hundreds of followers, whereas a small number of people will have in the millions or tens of millions. So degree skew, what else we got? The existence of hubs, which are just defined as large degree or otherwise structurally important vertices. So we're going to touch on this slightly later in a bit when we talk about centrality. Really, we're just going to be talking about PageRank. One of the special topics, a load of specials that we're going to throw into the mix. We're going to talk about centrality, which is kind of a measure of a hub. So generally, hubs are going to be considered, some definitions will say just, large degree vertices, but I like to include, structural importance or otherwise important in terms of information flow or diffusion through a graph. It's kind of what the hubs are. Regularity. So like all these properties apply to real world graphs, and they are going to come into play. We're kind of talking about stuff within the class, but again, most of the stuff we're going to touch on. We are going to look at some examples. That's why I'm touching on this stuff here. Just kind of introduce the notion, just get your brain kind of thinking about it. But it isn't going to be super important to the proof theoretical side of things, really. So we aren't going to be using the notion of irregularity to prove anything. We are going to talk random graphs. So we're going to be doing a couple proofs with that. So I don't know. Anyways, so these are going to come into play to an extent. That's kind of what I'm saying. But these are just more to get you thinking graphs and get you thinking about the connection between the real world and this theory stuff that we're going to be spending a vast majority of our time on. Not necessarily. So regularity, I don't know. The way I put it is not necessarily physically constrained. So this is kind of network specific. So if you think of a social network, you could be friends with someone in Australia or China or anywhere else, even if you live in New York. Basically, you don't need to be co-located. There isn't a physical constraint. You can be friends with someone on the International Space Station. There isn't a strict physicality constraint. For graphs that represent something actually physical, there is obviously, like a road network. You can't have a road that goes between New York and Australia or New York and the International Space Station. That'd be wild, But I don't know. Maybe there is. physically, maybe it is possible. Who's to say? Get one of those space elevator things. I don't know. Whatever. So small world property as well. Final thing. So what essentially the small world property is the notion that the average shortest path length is small. So to give you an idea here, if you've heard of 6 degrees of Kevin Bacon, that's this notion. Essentially, the number of hops it takes to get you from one object within the network, one vertex in the network, to any other vertex in the network is going to be small in general. And that's just a natural consequence of this like hubness, irregularity, degree skew. It's just kind of a natural consequence that arises. When we talk random graphs and one of our special topics, we will be looking at this in a little more detail. Essentially, this the regularity notion, everything else, the small world property kind of arises. And basically, so the 6 degrees of Kevin Bacon is, he was in a lot of movies with a lot of people. So if you define a like co-actor network based off of actors within Hollywood movies, so if two people are in the same movie, they share an edge is connected between them. The number of hops it takes to get to Kevin Bacon, I guess, is less than 6. The number of hops it takes to get from you in terms of like social relations to any other person on the planet outside of like, isolated tribes in the Amazon, I guess, is, I think it's like 5 or so. So from you to anyone else, for the most part. And this, well, I mean, not anyone else, but for a vast majority of people that exist, the number of hops is going to be 5 or so. The average shortest path between you and everyone else, only going to be like 5 social hops. You're friends with, someone in another class. They're friends with, someone in Europe. They're friends with someone in Australia. There's your connection to Australia. If you're not friends with that person I referenced in Australia, who's to say? All right, so this is kind of, real world graph stuff. So Facebook, so they like measure it every now and again. So I guess most recent is like 3.5, the average shortest path between, any, in terms of like all pairwise possible people on Facebook, the average shortest path's about 3.5 or so, I guess. So that's pretty small. So, average shortest path to me is infinity because I don't have Facebook. So, okay, where are we going next here? So let's talk. So we talk real world. Now let's get into the theory side of things. So let's talk history of graph theory. The history of graph theory. Well, so there's this place, there's this little town, I think in Germany or Austria, I forget off the top of my head. Little town called Königsberg. Königsberg. So it's got this river, you see. So we got this river in this town, and it's got a couple islands on it. So here's an island. So I'm not an artist. So that's waves in the river. Got a couple islands or otherwise land masses. And there's some bridges. So here's a bridge. There's a bridge. There's another bridge, another bridge. Or, yeah, so I have it drawn and I can't even decipher my own drawings. Okay, so yeah, it's pretty bad. Anytime I draw stuff, I immediately regret it. So just imagine this is a city with a river, and there's 2 islands on that river, and there's 1, 2, 3, 4, 5, 6, 7 bridges connecting it. So you can see kind of where a graph is going to be coming into play here. So there's this dude called Euler. So Euler, I don't know what he looked like. So we're drawing again here because I already drew, so I'm just drawing again. Looks something like this maybe. had some hair, probably. Maybe he was a happy guy. I don't know. He had some questions. He was asking himself, he's asking himself a lot of questions. You probably heard of him. He's always asking questions. He did a couple things. So what he asked was, can I start at one point in Königsberg, traverse each bridge exactly once, each bridge exactly once, and return to my start? So that was his question. So his question was, can I start at one point first each? So, you think about it. So he probably knew, intuitively that you can't, but he wanted to kind of figure out why he couldn't. So, I mean, if we tried, try to traverse here, just start little traverse. Obviously we failed there to traverse. Maybe we'll start on an island, traverse. Well, nope, failed there pretty hard. So it doesn't look like we can, but Euler, he was like, why can't I? So, his solution was to invent graph theory. Graph. So, you ever have a question, needs an answer, the solution is to invent an entire new discipline of math. That's what you got to do, I guess. So he invented graph theory. So he was as I like to say, the OG of GT. The OG of GT, Euler. So basically, obviously this is representable as a graph. So if we consider like the northern landmass, each island, the southern landmass, as well as the bridges connecting them, we have ourselves a graph. So really what he did, so we're going to talk about this proof later. We're actually going to prove it, but basically he invented the properties necessary within a graph for what we call an Euler Tor. So I don't know how to put this. So really, answer part 2, AP 2. Find properties of a graph for, this is what he actually did. To find properties of a graph that are required for what is termed now as an Euler Tor. I don't know if he called it that at the time. Basically it's started a vertex, traverse a bunch of edges, and end up where you started. Traversing each edge exactly once, end up where you started. What are the properties of a graph that are required to be able to do that? So now we call it an Euler Tor. Maybe he called it then at the time an Euler Tor, just because he could. Well, he's probably I don't know. I don't know what word for Tor is, and I guess German, or I don't know. Was he German? Maybe. Euler. Sounds kind of German. I don't know. Okay, so that's the history of graph theory. So that was like a couple hundred years ago. So graph theory has been around the block a few times. One of the older disciplines of math, I'd say. I don't know. Depends on how you define disciplines of math, I guess. But whatever. So let's actually get into some of the stuff for today. So really, like I said, today's going to be a lot of kind of definitions and such along those lines. So we're going to kind of formalize the notion of what a graph is and some of the terminology we're going to be using. So I already used some of the terminology and such, but it's used without whatever. Okay. So let me give you a little stretch here first. All right. So basic definitions. So basic definitions. What is a graph G? So how do we define a graph G? So graph G is essentially defined as a tuple, typically of vertices, which we define as a set, V of G. That G looks pretty whack. Let's fix that up a little bit. And edges, E, G. So our V of G is the vertex set, G. E is our edge set, G. And generally there could also be, associated, say, weights with vertices, weights with edges. So that would also be, part of this tuple. But for now, we're just going to keep it simple and just say define G as vertex set and edge sets. So vertex set, edge set. And for each edge, for each E within our edge set, G, our E is going to be defined between two vertices, U and V, where U and V are both within our vertex set of G. This is necessarily going to be the case. So we're going to have our edge set which has some number of E edges, some number of edges within it. Our edges are going to be defined as this relation between two vertices, arbitrarily selected as U and V, which are necessarily going to be contained within our vertex set. So for each edge, so we define our edges based off of the relation between two vertices. So those vertices aren't necessarily going to be unique. We're going to touch on because they could be defined as, a loop. Essentially, one edge can connect from one vertex back to that same vertex. So we're going to touch on that in a second. But there is necessarily going to need to be within each edge two vertices defining the endpoints of that edge. So terminology, min-null. So our terminology, U and V are endpoints of endpoints. So we're going to be using that quite a bit. E joins U and V. Probably never going to be using that one, really. It's in the notes for completeness, but I don't think I ever say that. U and V are incident. Incident with E. We could also likewise say E is incident. I usually use this on U, V. What else we got? Q and V are adjacent. Going to be using this one a ton. Just say U and V are, let's say to each other. To each other. So that's a very important one. So U and V are adjacent to each other. Also, likewise, as a synonym, U and V, I guess, I don't know. U and V are neighbors. We are neighbors. And so the notation we use for this is U within the neighborhood of V. V within the neighborhood of U. So this N of U defines the neighborhood of U. So basically, Basically, when we say the neighborhood of U, it's a set defining all vertices that are adjacent to that one vertex that we're considering. So the neighborhood of U would be a set containing all vertices that are adjacent to U, all vertices that are neighbors to U, all vertices that share an edge of which U is incident on. So, you know, the degree of V is its number of incident edges. So the degree of V is its number of incident edges. So there's a little nuance there we will touch on in a later class. But you might be thinking, oh, I mean, the cardinality of the neighborhood set of V must be equal to. So we define degree of V as d of V. So here, this is the notation we'll use to define the degree of V. You might be thinking that, and you're kind of right, but not necessarily. Only in simple graphs. So what is a simple graph? Man, there's a lot of terminology here that we're getting into. So, I skipped order and size. So I mean, I really never used that. So we'll define simple graphs in a second, but just to keep in line with the notes, I guess. Let's say that order of G equals cardinality vertex set of G, which for simplicity, I use the variable n. So that's fairly common to use. The size of G equals the cardinality of the edge set G, which we will be using M to denote. Yeah, sometimes I might be writing out a proof where I label a vertex n, and it inherently annoys me because we're using the variable defining the order of G. I mean, I'm not really going to be defining saying the order of G very often. I'll usually just say, the number of vertices, cardinality of the vertex set. This is my preferred terminology. But if I ever throw that out there, then, there we go. So what we got? We got a lot. Yeah, I mean, it's a lot of definitions. You might be thinking, this is painful. It's not a super fun time for me. See, when we get into the proof stuff, it's a little more enjoyable. Order of G, only simple graphs. Let's see. So, just thinking about how to organize this. I guess we should stick with just going to stick with the order given in the notes. So I have some other stuff written, but it's all out of order. So I'm just confusing myself. Happens a lot. So what we got? So the order of G, size of G. So if it says, we aren't going to be. So I also say in the notes, the order and size are finite, then G is finite. I mean, every graph we're going to be talking about is finite for the most part. So yeah, and this PQ graph, never use that terminology. So I'm just going to skip that. So multi-edges, let's talk multi-edges. So we need to define multi-edges before we can define a simple graph. We need to define multi-edges and self-loops. So multi-edges are let's say are edges that have edges in G, let's say edges in G that have the same endpoints. endpoints. So if we consider our edge E up here, so E is defined between U and V. There could be some edge F, also U and V. No, those two edges would be multi-edges. Wow, nice. Multi-edges are edges in G that have the same endpoints. So e.g., egg example, E equals U, V, and F equals U. Those would be multi-edges. So E and F are multi-edges. E, F are multi-edges. Self-loops are edges. Self-loops are edges in G. Let's do singular formulation here. A self-loop. Self-loop in G is an edge that connects the same vertex to itself. E and G, this self-loop E, just connect U back to U. I think we could draw this out too. All right, so we could draw a multi-edge here as such. We have our U, V, and E, and F. Then we have our self-loop here. We have U and our edge E connecting back to itself. Edge E. Oh, black there. Edge E. So we have self-loop multi-edges. So now we've suitably defined enough things that we can go back and define a simple graph. A simple graph has no multi-edges or self-loops. Self-loops also just commonly called loops. So we have a simple graph, a loopy. So this is not in the notes, but I think might as well just define these two. A loopy graph, since I use this terminology on occasion. A loopy graph has self-loops. A multigraph has obviously multi-edges. So I might say a loopy multigraph. That would mean a graph that can have loops and self-edges. Or I mean, it can have loops and multiple edges. Multi-edges. Or multiple edges. Same thing, but different word. So we have simple graph, loopy graphs, and multigraphs. And what else we got? So these will come in these other. So we more graph classes in the mix here. Oof. It's getting sore from all this graph talk. Let's go on. Let's actually do that. So cardinality of the vertex sets and cardinality. So sometimes I don't do the full E of G, V of G stuff. So if I just say V, that's inherently defining the vertex set of some graph. It's just shorthand notation. They're less than infinity. G is finite if cardinality of V and cardinality of E equals 0. So underline that. G is null. So some other notation that we have is we could say, or empty set. So if the cardinality of a set is 0, equivalently, that set is equal to just, empty set. Yeah, it's the 0 or the O with a slash in it. That's how we define an empty set. If cardinality of V equals 1 and cardinality of E equals 0, G is trivial. And then if cardinality of V greater than or equal to 1 and cardinality of E equals 0, G is empty. So inherently, any trivial graph is also going to be an empty graph. Any trivial graph is going to be a finite graph. That's how it is, I guess. All right. We're doing pretty good time-wise here, actually. How'd that get selected? So G is empty. Okay, so let's keep her going, I guess. I'll hit the chat, see if we had anything I missed. I'm too busy writing hard here. Now, is there formula for measuring the average number? So the way you'd measure that, they didn't do it this way because it would be computationally infeasible to do it this way. The way you'd measure the average, so really what that measurement is, so I'm going back to the chat from 20 minutes ago, where the average number of hops between any two people is 3.5. So really it would be computing all pairs' shortest paths, taking the average shortest path's length. So from every person to every other person, compute the shortest path length, which is a linear time algorithm. Do it for all pairs, end up with a quadratic time algorithm for, in the billions. It's a lot of shortest paths to compute. So it's unlikely they did that, but there's a number of good approximation algorithms that would compute that. So yeah, it's really just the shortest paths problem is how it's done, how you'd measure because really that's just computing the average shortest path's length. If you're computing the average number of connections between average number of hops from one person to another in a network. So that's that for us. Okay, going back to share mode. I could just hit Control-Shift-D. Let's try that out. Says. Oh, okay. Still got to push the button now. Doesn't really save much time. All right. Yeah, another stretch. Take a stretch break here. Take a sip of coffee. Yeah, so I'm trying to decide how far we should go. Should we get through? I think we could get through. Yeah, I think we can get path, bipartite complete graph, subgraph. And talk a little bit about this networking stuff. I think we got time for that. So let's hit it. Nice. G is empty. All right, so let's delineate a new section here. So I don't know what we'd say here. Let's say graph types or something. I don't know. We already kind of did that. But yeah, we don't need to label our sections. We don't need to arbitrarily constrain ourselves in terms of the format of the notes. So let's talk path. So we're going to be talking paths quite a lot. So what is path? Path is a simple graph you're in graph mining, we already talked paths in terms of connectivity. So we're ahead of the game. Except we didn't define simple graphs or, give a formal definition, but, now if you're coming from graph theory or graph mining, now you learned. So these classes work well together. So everyone should take them both at the same time. Maybe, I don't know. If you're in math and have no CS background, you probably shouldn't take graph mining. I would recommend against it. So path is simple graph. Oh man, this definition I have in the notes is cumbersome. Is there a way to simplify it? I don't know. Whose vertices can't be listed. Can be listed. So this is good because we can throw in some new shorthand listed ST, such that we're going to be throwing that one down a lot, such that any two vertices. So for what a path is, it's a very simple concept. This definition, I should probably rewrite this definition so it isn't so cumbersome. Any two vertices are adjacent. If, so when I say if, what that means is if and only if and only if they are consecutive. How do you spell that? It's definitely no Q. Consecutive in the list. So this is cumbersome, I admit. It's definitely got to be a way to simplify that, but let's just consider a path. So here we'll define P. So we have a simple graph. A, B, C, and D. There's a path. Simple, right? So we can list. So what we say, we're listing consecutively in some list. We could define this path. So we could define it in a couple ways. One way we could just define it if we're considering just a path on a simple. So usually when we talk paths, they're going to be a subgraph, which we'll define in a second, of some other graph. We could find the path as vertices A, B, C, D. Generally, if we're considering this path as a subgraph and say a multigraph, we'd also have to inherently consider the edges on this path, because if we had multiple edges, so if we had another edge H here, we could have a path that goes from A, B, C, and D that follows edge F or follows edge H, but it can't follow both because the path is inherently simple graph. So it's a simple graph that starts at A, starts at some vertex, ends at some other vertex, traverses some number of edges. And as it is a simple graph, so one of the restrictions here is adjacent if and only if they're consecutive in the list, meaning basically when we have this as a graph, we'll get there in a second. Let me first finish the first thought that I was having. So we could list it in terms of the edges as well. F, C, G, and D. So we could define a path in terms of the edges or the vertices itself if we're, say, considering a path as a simple graph, or a path as just a path as a graph itself, or if we're considering a path within some multigraph. Then we would also have to necessarily consider the edges as well that go in between the two vertices, because there are multiple options. We can only select one because our path is a simple graph. So we can, we can't have multi-edges in a simple graph. Basically what we're saying here. All right, let's just move on. Okay, let's talk cycle now. So cycle, a simple graph. Simple graph with an equal number with an equal number vertices and edges. And edges, another cumbersome definition here. Equal number of vertices and edges. I gotta rewrite these definitions. These are, I don't know. I think these are bad. Whose vertices can be placed in a circle. I think I maybe copied these from the book, but I don't like these at all. Vertices can be placed. I think just intuitively there's got to be much simpler. Could be, but we'll stick to what the notes say, just for now. And obviously, intuitively, I think they're simple enough that we don't simplify the definition. Could be placed in a circle, I guess. Circle. And placed in a circle and two vertices. With these definitions, maybe we aren't going to have time to do everything. Writing these out. Two vertices are adjacent if and only if they appear consecutively. I apologize for this. Along that circle. Okay. I guess. So obviously, cycle. We have some vertices in a circle. Oops. It's about to write A. Instead I drew the vertex as A, B, C, D, and E. They're adjacent. Simple graph here. Wow, look at that cycle. It's just a circle of vertices, all connected together in a simple graph fashion. So here, we call this C. And likewise, we could also define C as A, B, C, D, E. And then we could, depending on your preference, you could just, throw that A back in the mix as the next vertex, or not. If you omit it, it's inherently implied that C can be defined in this list, and it ends, since it is a cycle, it ends back on A. Note, and also, so I will use this terminology repeatedly, and also be called closed control that H, closed path. So essentially when we close a path, we end up where we started. So that inherently, a closed path and a cycle are just synonyms. They mean the exact same thing. But a lot of the time in the context of proofs, we'll be saying, we have this path, it's possible to close this path to create a cycle. But, formally, I don't think closed path is real terminology. Closed path just means, so whenever we say path, it inherently implies an open path. So when we close it, it's inherently a cycle, but within the context of proofs, I will tell you right now, I will be saying we're going to be closing some paths. This is or is not a closed path, or conversely, an open path. I mean, saying an open path is redundant, I do admit, but within the context, open versus closed, it's useful. Or whatever. All right. So we have a path. We got a cycle. One more thing. Find a tree. So here we have a simpler definition. Tree, a simple graph. Connected graph. We got the word connected. I didn't define that yet. Simple connected graph with no cycles. And we're connected. So we'll talk connectivity. We already talked it in graph mining. If you aren't taking that class, you missed out. But yeah, we'll talk more. We're going to spend a lot of time talking connectivity here in this class as well. A connected graph is a graph. So let's say connected graph G. Let's say connected graph G for all u, v, then the vertex set of G, there exists what we define as a UV path. So for all UV within our vertex set of G, there exists a UV path. So we're talking, so this upside down A guy, if you aren't familiar with that notation, is for all we define in, so that backwards E, backwards lowercase e kind of thing, defines, is essentially saying in. So for all UV pairs in our vertex set of G, this big backwards E guy, that means there exists. So for all UV in our vertex set of G, there exists a UV path. So a UV path, as you might inherently think, from U to V. So when we say a graph is connected, what we're saying is for all possible pairs of vertices, there's a way to get from that U, some U to some V. So within a tree, the graph is connected. It's simple and it has no segments. I'm sure all of you are familiar with trees, maybe not formalized in this way, but you probably, now you got the formal definition. I mean, a lot of this stuff, the intuitive notion is quite simple, but when we start formalizing stuff, we have to be a little more careful. And, you know, as someone with an applied background, I very rarely am careful, so feel free to call me out when, you know, I don't consider trivial graph in my definition, or I don't consider, you know, the possibility of an infinite graph or something. And usually people call me out anyway, so, you know, I'm used to it. Yeah, but I'll address it and fix it. It's easy to do so with this OneNote stuff, so pretty straightforward. All right, so should we get into clicks or not? Let's got some. Where did that come from? What are we talking next class? We're talking isomorphism. We got about 20 minutes. You know, I don't think we'll have enough time to talk both, define all the rest of this stuff, and start talking network X. So what we're going to do is we're going to talk network X, so we're going to put off those definitions till the next class. That's what we're going to do, and then we'll have, you know, we'll get into that. And maybe, you know, we probably won't need more than like 5 or 10 minutes for the network X stuff. So we'll probably end a little early today. I think that'd be the way to go. That's the plan. Okay. So, you know, hopefully that doesn't throw off the schedule that I said was locked in, but, you know, who's to say? Who's to say? I mean, the definitions are already there, so you could probably just read them anyway. So I don't think it's super critical. A lot of this stuff's pretty straightforward. Let's draw out the connected graph. I mean, again, so let's draw out all of these and then we'll get talking network X. How's that? You know, that sounds good. So let's say normally, let's say. So when I talk trees, I'll normally define them as the word T. So there is some confusion that occasionally arises with people that are coming straight out algo when we're talking trees. So they normally think the concept of, normally the context with a lot of the trees you've worked with, like algo, data structures, whatever, are rooted trees, especially probably more so in data structures than algo. Again, I don't really know the full context of both those classes, but I'm just, you know, assuming from the things I've observed in this class. I'm inferring. So it's, you know, a lot of people, you know, we talk trees. A lot of people think there needs to be a root or anything. If there is a root, we would call it explicitly a rooted tree. We are not going to be dealing with rooted trees very much in this class. there is the possibility of using the notion of a rooted tree in various proofs. TBD if any of those proofs will be asked of you. Where we can use the notion of a root within the tree to kind of prove something, like a path length or this or that. But generally speaking, a tree is just going to be, what you think of as a tree, a graph that's connected without cycles. So there also is the notion of a forest, which is a disconnected acyclic graph, but we aren't going to touch on that yet. We're going to spend a lot of time on those later, but it's good to kind of get a taste for it right now. Start of this stuff. So tree T, as we see right there. What else do we say? Connected graph. So let's consider graph G. If we would have graph G here, so this is just an arbitrary connected graph. As we got some action going on there. Bow tie in the mix. So G is connected. So connected. Because if we consider between all possible UV pairs, so if we have our U here and our V here, there exists a path. Some arbitrary path between them. It doesn't have to be necessarily a shortest path. This one is not. But there exists at least some path that connects them. If G, let's say hypothetically, if G did not have that edge, how do we get there? I don't know. So you can't do that though, because by our definition of a path, the vertex here and a vertex here must be connected, must be adjacent to each other. So they are not in this instance, so G would be, as we would term, disconnected. It would have two connected components. Throw them back to graph mining again. We've got connected components. But basically, obviously here, so there does not exist between this specific pair of vertices, V and U, there does not exist a path, then disconnected. Wild stuff. All right. Anything? Oh, let's talk UV path too. One more. One final one. So if we consider our, let's do one of these. Copy paste. I think I gotta push that. Hit the old copy. Copy. Hit the paste. Yes. Right. Doing some fancy techniques here. So imagine we have our other G here. Okay. Lock it in. How do you lock it in? So G. Okay, just. It didn't. It's all whack. Guess I need to keep source formatting or something. I don't know what I pushed. So the whole point was to have a UV path. So G is now connected. And we have our, too far with that edge, our UV path, or our VU path equivalently. Yeah, directionality really doesn't matter here because we aren't considering directed graphs yet. Not for a few classes will we start throwing arrows on our edges to direct them. Now we're just, each edge looks equivalent from essentially both endpoints of that edge. Cool stuff. Okay. All right. Let's let me get into typing mode here. And we'll look at the network X stuff and then we'll be done. Oh man, so many wires. So pretty late, but at least you made it. Just in time to get let's get rid of that. Okay. All right. So, I mean, we aren't gonna I'm not gonna be assigning any coding stuff, but we are gonna be looking at on occasion when we have time examples in practical applications. So really, like a lot of the special topic stuff. So we're gonna be talking PageRank. So every year we predict the Super Bowl winner to glorious accuracy. Nailed it several times. Called the underdogs by the power graphs. So it's one thing I like to do. So we'll be doing that. And then there's, random graphs epidemiology, which might be kind of touching on some more of this stuff. So it's good to, at least demonstrate it and such. Okay, where's the code? So what we're going to be using here is Network X. So this is probably the most popular. Might be, I need to do Python 3. It's probably the most popular graph library that exists, to my knowledge. So this is for Python, so if you have Python, it's really just pip install Network X, you're done. Depending on, various things, I guess. I don't know. But really, should be done. Boom. Good to go. So we have this test.data. So yes. So this is representing the bridges of Königsberg, actually. So this is representing that one graph that we originally looked at. I don't know how the vertices/edges are labeled specifically. No. So 0, 1. So you could probably map that out on your own, if you want. But basically, there's some label, so that might be 0. Well, so 0, 0. So vertex 1 has degree 3. So you can kind of map it based off of degrees, probably be the easiest way. Wait, that can't be right. Yeah, that is not right at all. So I think I copied the wrong thing, maybe. Oh, well, okay. Well, that one's on me. We're still going to see what happens here, and you get the idea. So your task for today is to actually write in the actual bridges of Königsberg graph. So this would be called what we term as an edge list format, where essentially we just, as a list, we list the edges. So 0, 1 defines an edge between vertex 0, vertex 1. 0, 5 defines an edge between vertex 0, vertex 5, etc. So here we have 1, 2, 3, 4, 5, 6, 7, 8 edges. And so we have up to 0 through 5 vertex labels, meaning we have 6 vertices, 8 edges. And we're going to see if we can do an Euler tour on this, which is not representing the bridges of Königsberg. I think maybe, so I copied this from last year. I think what happened was I originally had bridges of Königsberg, then I modified it for more examples, and I never modified it back. So we got what we got. So, all right. My apologies if you really wanted to see the existence of an Euler tour. Let's, wait, we need to copy paste this in first. So there we go. Hit up the old Python 3, import our old Network X. We're imported. So what do we do next? Gonna read that data file that we just wrote, that edge list of test.data that we just wrote. Read it in, create RG. So we'll read that edge list, construct the essentially data structure representing our graph, and we can look at some properties of the graph. So we can look at our order, as we defined as the number of vertices on our graph, which should be 6, hopefully. Our size should be 8, if I recall correctly. Then we could print out our nodes. We can also print out our edges. I'll probably add that in the mix just for, fun, I guess. So we got our 6, we got our 8, got our nodes, got our edges as a list. Our adjacency structure, so essentially this just lists the neighbors of each vertex, the vertices of which one vertex is adjacent to. So vertex 0 is adjacent to 1, adjacent to 5. Vertex 1 is adjacent to 1, adjacent to 2, adjacent to 3, and adjacent to 4. Wow, this is vertex 1. It's a hub in this graph. Vertex 5, adjacent to 0, 3, 4, etc., etc. And so, it has all this other extra stuff. So that's just like associated with labels and whatnot, for the, that we don't have. I think that would define the edge labels. If we had one, they would be kind of listed in there, but we don't have that. We don't have labels for edges. We just have edges as is, nothing fancy. And got our edges. Pretty cool, pretty cool. Now we could do some loops here. I don't think this is going to work. Let's see what happens. Sometimes copy pasting, it works. All right. Sometimes with copy pasting with the tab stuff, it doesn't work nicely. So basically, this is just printing out our edge list. But here, as we are an undirected graph, each vertex, regardless of which side of the edge you're on, is going to look equivalent. So this is really just printing out each edge exactly twice from the perspective of each vertex. So what we're doing here, we're going through our vertices, we're looking at our neighbors, we're printing that neighbor. So each vertex is going to print out its neighbors 0, 1, 0, 5, 1, 0, 1, 2, 1, 3, 1, 4, etc. And then obviously from the other perspective, since 0 is adjacent to 5, or 5 is adjacent to 0 based off of this adjacency list, equivalently, 5 is also adjacent, or 0 is also adjacent to 5. So yeah, down there. So the reason these are out of order is because, they aren't listed in numeric order. When NetworkX parses them, it just parses them as essentially strings. So vertex labels, not necessarily like vertex numeric identifiers or anything. So inherently, when it constructs the vertex, I don't use the word nodes, I use the word vertex, representing 5, it'll be, it's essentially the label there. Internally, it probably has, the identifier as, 0, 1, 2, 3, 4, 5, but, with the associated character string label of, as is given. Okay. Then we could also do like Eulerian stuff. So Eulerian circuit is equivalent term for an Eulerian Tor, so we could just run that. So as I mentioned, so there's a lot of reactions going on. Okay. I never noticed that. Okay. Oh, okay. No. Oh, no, sorry. Okay. Okay, all right. I don't know. Yeah, I don't know what happened there. So sorry about that. It's only been 5 minutes though. So it's if you remember what I was saying there, we did pretty much this stuff. Yeah, so I guess the comments weren't showing up anymore. Or I guess since I wasn't sharing, they didn't flash up. Since I didn't notice I wasn't sharing, it's, it got all messed up. So as I said, we read in the data, we printed some stuff. We printed our, okay. All right, so I think we have time to just start from scratch. So I don't know where, so basically we have NetworkX within Python. We have our data set, which is not representative of that graph because it was modified previously. These are all recorded, yes. And yeah, so basically we read in our data, pretty straightforward. So this would be our edge list format, where we list essentially our edges 0, 1, 0, 5, 1, 2, 1, 3, 1, 4, 2, 3, 3, 5, 4, 5. Those are our list of edges. This is called the edge list format. So we read our edge list, create our G, which is our Python or our NetworkX data structure representing our graph. We print out our information, our order, call number of vertices, cardinality of the vertex set, our size, cardinality of the edge set, our nodes themselves, our adjacencies. We loop through and print, and we are going to run our Eulerian circuit. So, as was already done here, print our order of the graph, 6, print our size of a graph. If we would print the number, the nodes, so here we have essentially the node labels. What I was talking about was the vertex. So these are, not in any necessary order. These are listed in the order that they are encountered within that edge list file. So these are character identifiers. So essentially when NetworkX parses a file, it reads them as strings, the labels as strings instead of numeric identifiers, unless you explicitly tell it to. So that's why, they aren't in assorted order as you would expect. Because essentially under the hood, they probably are. So under the hood, this 5 would be represented probably by the actual identifier of 2 within the actual data structure represented graph. But really now this works with generally just, like a mapping 5. Essentially, that's just the label of the vertex. So how you consider it. Our adjacencies. So 0 is adjacent to 1 and 5. 1 is adjacent to 0, 2, 3, and 4. 5 is adjacent to 0 and 3, et cetera, et cetera. So this is just listing the neighbors of each vertex when we say, we look at our adjacencies. Edges, just, again, list of edges. So when we go through all of our vertices, this is just a common way to loop through vertices, neighbors, et cetera. Like examine the structure of a graph or perform some operation or algorithm or whatever. Really here, we're just printing out the vertex labels. So 0, 1, 0, 5, et cetera, et cetera. The reason why these edges are listed twice is, as I mentioned, they're undirected edges. So from the view of edge, say 0, 1, 0 has neighbor 1, so 0, 1, and 1 has neighbor 0, 1 and 0. There we go. And let's actually run that Eulerian circuit, see what happens. We'll run this. I'll look back to the chat. See, I saw there was a lot of people saying that they can't see the screen. So I don't know, not sure what happened there. I think, so yeah, I don't know what happened. I think maybe when the thing got disconnected, it broke it or something. I don't know. So we don't have an Euler circuit because G is not Eulerian. Wow, just like our bridges of Königsberg. Nice. Nice stuff. But we can, what we can do is import matplotlib and plot our graph. See why it's not Eulerian. And we'll show it. Okay. Just plot.show. Whoa, look at that cool graph. Definitely not Eulerian. I wonder why. You'll just have to wait and see. You'll have to wait and see why. There's a reason why, but we'll prove that later. It has to do with a couple of these guys. And all right. Yeah, I mean, if we try to find a tour, we can't. We can't. Yeah, definitely can't. Too bad. Okay, now let's actually intentionally stop sharing the screen because class is at an end. Basecam, no, can't see your screen, can't see, hello, can't see, can't see. Pretty face. All right, yep. So okay, content as term. These are recorded, yes. There will be, we're in record mode. Recording is in progress, as it says. I should be good to go. All right. So yeah, apologize for those technical difficulties, but that's just life in virtual reality. All right, so okay, classe ist zu Ende. For a little German out there, keep with the theme. Okay, so if there's any questions, just hit up the chat. Technically do have office hours, so I guess I'll just start my personal room. So I don't know. Office hours, my personal room. I don't think they'll be necessary, but I'll just have it open. So yeah, okay. And those will get uploaded probably later today. All right.